Hey everyone, welcome to The Explainer. Today, we're basically putting on our scientific detective hats to investigate a pretty massive mystery, and it's one that's hiding literally right in plain sight. We're going to question the actual reality of the seemingly simple objects around us. I mean, is the matter around us actually pure? Let's uncover the hidden science of everyday objects. Okay, so here's our structural roadmap for today. We're looking at 5 key areas. First, the illusion of purity, then the mixture spectrum, the art of unmixing, physical versus chemical changes, and finally, the truly pure substances. We're going to start with the messy, everyday world of mixtures, and then just zoom all the way down to the fundamental, truly pure building blocks of matter. All right, kicking things off with Section 1, the illusion of purity. What does pure actually mean? Think about the last time you went grocery shopping. You see it everywhere, right? Marketing labels have completely distorted our scientific understanding of the world. So, let me ask you this. Is your quote-unquote 100% pure milk actually pure? Well, a scientist would look at that exact same carton and tell you absolutely not. In reality, it's a wonderfully messy mixture of water, fat, and proteins, all blended together. So, the absolutely crucial point here is how we define pure in science. True scientific purity means a substance consists of a single type of particle, and they are all exactly the same in their chemical nature. Because of this really strict rule, true scientific purity is incredibly rare in our everyday lives. I mean, from the soil in your garden to the seawater at the beach, almost everything we interact with is actually a mixture of 2 or more pure components. Moving right along to Section 2, the mixture spectrum. Now that we know most things are mixtures, we kind of need to categorize our suspects, right? Scientists divide mixtures into 2 broad camps, really based on how evenly their ingredients are blended at the microscopic level. On one side, we have homogeneous mixtures. These have a uniform composition throughout. Think of salt, completely dissolved in a glass of water. You can't see the salt anymore, it looks exactly the same from top to bottom. On the other side, we have heterogeneous mixtures. Now these have physically distinct parts and a totally non-uniform composition. A classic example here is oil and water. Literally, no matter how much you shake it, they just separate right back into distinct layers that you can easily see. Now, consider something we interact with every single second, the very air we breathe. You might not intuitively think of an invisible gas as a mixture, but air is actually a perfect example of a homogeneous mixture. Specifically, it's a gas-in-gas solution made up of about 78% nitrogen, 21% oxygen, and small amounts of other gases. Because it's perfectly uniform, every breath you take provides that exact same, reliable chemical blend. But what happens when a mixture is somewhere in between? Enter colloids, which brilliantly demonstrate something called the Tyndall effect. When you look at sunlight piercing through a dense forest canopy, or even just a laboratory beaker under a light, you're seeing it in action. In a heterogeneous colloidal mixture, like mist in a forest or even a few drops of milk in a glass of water, the microscopic particles are suspended. They're way too small to be seen individually, but they are just large enough to scatter a beam of light passing through. It literally makes the physical path of the light suddenly visible. And honestly, colloids are absolutely everywhere. Everyday items like shaving cream, cheese, and even automobile exhaust are all categorized as colloids. Scientists classify them based on what phase is dispersed within what medium. So for instance, a liquid dispersed in a gas creates an aerosol, like fog, while a gas dispersed in a liquid makes a foam, like shaving cream. All right, Section 3, the art of unmixing. Okay, we've established that our world is fundamentally a giant world of mixtures. But here's a puzzle for you. How do scientists reverse engineer them? Just think about this for a second. How do we get the dye out of black ink? If you have a single drop of black ink from a fountain pen, how could you possibly unmix it to see what it's really made of? It seems impossible, right? But chemists actually have some incredibly ingenious separation tools at their disposal. Enter chromatography. This is so cool because of its elegant simplicity. You basically place a drop of ink on a strip of filter paper and suspend it just barely above water. As capillary action naturally draws the water up the paper, the water acts as a sort of physical vehicle. Because black ink is actually a mixture of different colored dyes, and those individual dyes dissolve in water at slightly different rates, well, the water physically drags the more soluble colors faster and higher up the paper. Suddenly, that single black drop separates into a beautiful rainbow of its hidden component colors. It's like magic, but it's just science. Now, what if you need to separate 2 liquids that are completely mixed together, like, say, acetone and water? For that, we use distillation. If you look at a specialized setup, you'll see a fractionating column packed with glass beads. This is a crucial upgrade to simple distillation. We use this when we're separating miscible liquids whose boiling points are super close to one another, like less than 25 Kelvin apart. Those glass beads provide vital extra surface area for the vapors to cool and condense repeatedly, which ensures a highly precise separation. And we can actually take that exact same concept and scale it way up for massive industrial applications, literally unmixing the air we breathe. To obtain pure gases from air, scientists first compress and cool the air to extreme temperatures until it actually turns into a liquid. Then, they allow this liquid air to warm up super slowly in a giant fractional distillation column. Because gases like nitrogen and oxygen have slightly different boiling points, they boil back into a gas and separate at distinct heights in the column. That allows us to harvest them in purely isolated forms. Let's pivot a bit to Section 4, Physical versus Chemical Changes. Let's shift our focus to the fundamental rules of matter. What happens when we just mix things together versus when we actually change what they fundamentally are? Well, a physical change alters the state or appearance of a substance without changing its chemical composition. Melting ice or dissolving salt, those are physical changes. The water is still H2O, the salt is still salt. But a chemical change, that literally rewrites the chemical identity of matter. When you burn cooking oil, it chemically reacts with oxygen in the air to form totally new substances with entirely new properties. You can't just cool the smoke and get your cooking oil back. Let's apply this. The source text gives us a fascinating challenge. During burning of a candle, both physical and chemical changes take place. Think about that for a second. How can it be both at the exact same time? Well, the melting of the solid wax into liquid wax is a physical change. It's still wax, just in a liquid state. But the burning of the wick and the vaporized wax reacting with oxygen to create heat, light, and carbon dioxide, that is a definitive chemical change. And finally, Section 5, the truly pure substances. Our scientific detective work has finally reached the bottom floor. We are looking at the foundational, truly pure substances of the entire universe. At the very base level, we have elements. As defined by the pioneering French chemist Antoine Lavoisier, an element is a basic form of matter that absolutely cannot be broken down into simpler substances by chemical reactions. Elements are the purest, most unbreakable building blocks of literally everything we interact with. And they come in different flavors too. Lustrous, conductive metals like gold, nonmetals like oxygen and carbon, and the in-between metalloids like silicon. And here is a number that should absolutely blow your mind: 92. Out of all the incredible, staggering diversity in the known universe, from the stars in the sky to the screen you're looking at, right down to the cells in your own body, there are only 92 naturally occurring elements. Just 92 fundamental building blocks that combine to make up absolutely everything around us. It's kind of like a giant cosmic Lego set. When these elements get together, they can do so in two main ways: as mixtures or as compounds. In a mixture, elements just physically mingle. They have a variable composition and retain all their original properties. But in a compound, elements chemically react and bond together in a strict, fixed proportion. And the results are wild. If you just physically mix iron filings and sulfur powder, you get a magnetic, yellowish mixture. But if you heat them up and force a chemical reaction, they create iron sulfide. That's a brand new compound that smells like rotten eggs, has a totally different color, and completely loses its magnetism. What we have here is a perfect visual summary of the entire macro to micro journey we've taken today. We started at the top with just matter, saw how it breaks down into pure substances versus mixtures, and then we followed the trails all the way down to elements, compounds, homogeneous solutions, and heterogeneous suspensions. Basically, everything you have ever touched, seen, or breathed fits somewhere perfectly into this hierarchy. So, we've solved the mystery. Purity in science is incredibly specific, and our everyday world is vastly more complex and mixed up than it appears at first glance. I want to leave you with this challenge. Look around your room right now. Seriously, take a look. Based on what you've learned in this explainer, which of the objects you see are just mixtures, and which ones could actually be truly pure substances? Keep your scientific detective hat on and keep questioning the matter around you.